Today's most incredible aircraft, they're not born in a hangar. They're born in the digital world. They're crafted from millions of lines of code and pushed to their limits in super powerful simulations. But here's the thing, a perfect virtual flight is only the beginning. The real test, the one that really counts, happens up in the sky. So welcome to the high-stakes, high-pressure world of the flight test engineer.
So here's our flight plan for this explainer. First, we're going to talk about why this job even needs to exist. We'll call it the simulation gap. Then we'll dive into the three main types of test missions. We'll look at the engineering blueprint they follow, see how the whole team executes the plan, and then we'll go inside a typical day for an FTE. And finally, we'll wrap up with why this role is just so incredibly important.
All right, let's get right into it. We have to start with the fundamental problem, the very reason this whole profession is absolutely necessary. I mean, it's a totally fair question, right? We've got supercomputers that can model almost anything, but when you're talking about a multi-ton machine hurtling through the air with people on board, almost just doesn't cut it. And this right here is the heart of the problem. Research from places like NASA makes it crystal clear. Even our best simulators have big limits. You just can't perfectly replicate the chaotic, unpredictable reality of flight. You've got dozens of complex systems all interacting in ways you can't always predict. So these gaps between the digital model and the real world, they're not just a possibility, they're pretty much a guarantee. So this is where the flight test engineer, or FTE, becomes the hero of the story. Their entire mission is to bridge that gap between what the computer predicts and what happens in physical reality. And that mission really breaks down into three core types of tests. First up, you've got experimental testing. And man, this is the stuff of movies, the stuff of legends. This is about pushing the absolute limits of what we think is possible. Think Chuck Yeager in the Bell X-1, literally flying into a total unknown to see what happens when you smash through the sound barrier. It's all about proving or disproving a brand new idea in aeronautics. Next, you have development and certification. Now, this is the bread and butter for most FTEs. It's less about exploring some wild unknown and way more about proving what you think you know. The goal here is simple but intense. Rigorously prove that a new aircraft is safe, that it's reliable, and that it does exactly what the designers promised it would do. And finally, there's production testing. Think of this as the final quality control check. This isn't about testing the design itself anymore. It's about making sure that every single plane that rolls off that assembly line has been built perfectly and is 100% ready for safe delivery to a customer. Okay, so with all of this risk and complexity, you might be wondering, how on earth do they manage it all? Well, it's not like they just go up there and hope for the best. No way. It is a highly structured, super disciplined process. They use what's called a systems engineering approach, and you can think of it as a crawl, walk, run method. You start with super clear objectives, you iterate on the design, and then, and this is the crucial part, you verify every single component, every little subsystem on the ground before you would ever think about testing the whole shebang together in the air. And this is a perfect example of where those ground-based tools come in. Simulators, structural load tests, avionics benches, you name it. They are absolutely essential for that verification step, that walk phase. They let engineers and pilots test everything in a safe, controlled environment. But they are not the final word. And this distinction is so important. Ground verification is all about control. It's about testing the knowns in a predictable lab environment. In-flight testing, on the other hand, is all about reality. It's about encountering the unknowns and seeing how the entire, fully integrated system actually performs when it really, truly matters. All right, so the plan is set, the parts have been checked and double-checked on the ground. It is time to fly. But the FTE isn't a lone wolf up there. They're a key part of a highly specialized team. A typical flight test team is just a marvel of collaboration. You've got test ops, who are kind of like the conductors of the orchestra, directing the entire mission. Ground ops is laser-focused on the health and safety of the aircraft itself. Instrumentation, they're the geniuses who make sure every single critical piece of data gets captured. And then you have the analysis engineers, the deep specialists, watching their specific systems, like the wings or the flight controls, in real time. So let's step into their shoes for a minute. What does a day in this high-stakes, high-pressure environment actually look like for the engineers on the ground? Okay, so the day kicks off way before the engines even start to spin up. It starts with a comprehensive briefing. Schedule, weather, objectives, you name it. Then it's out to the aircraft for incredibly meticulous pre-flight checks. The flight itself, That's hours of intense, unwavering focus. And once the plane is safely back on the ground, the work is far from over. Now it's time for the debrief and the really deep dive into terabytes of data. And you can bet this isn't some casual gig. It is super regulated. Authorities like EASA, that's the European Union Aviation Safety Agency, they have formal categories for these engineers. And engineers' qualifications literally determine the level of risk they can handle, all the way from a Cat 4, who might verify a minor change, up to a Cat 1, the person who gets to work on those mind-bending experimental flights. But for all those formal structures and regulations, sometimes you just need a dose of gritty reality. And this quote from an aerospace engineer on Reddit, it just nails it. It says, open up some FEM results, that's a kind of stress simulation, realize everything is shit, copy-paste it into a new version file, spend a couple hours edits to try to make it less shit. That is problem solving at its most raw and honest level. So after all of that, the complex simulations, the long hours, the data crunching, what's the big takeaway? Why does this role matter so much?
It really comes down to one thing. They are the final guarantee. Their work is the last line of defense. They are the ones who ensure an aircraft is truly safe and performs exactly as it's supposed to. Every single time you or I get on a plane, we are putting our trust in the precision and the absolute dedication of the FTEs who signed off on that design. And at the end of the day, this field is just filled with people who feel a massive sense of responsibility. I mean, look at this number. This is from just one major company, Lockheed Martin. Over 850,000 hours volunteered annually. That shows a culture of people who are committed to making an impact, a mindset that is absolutely essential for a role where the stakes are this incredibly high.
And that brings us right to the edge of what's next. We're all seeing this massive shift in aviation, with electric propulsion and more autonomy. So the question we want to leave you with is this. In a future that's becoming more and more virtual, how will this critical, hands-on role of validating reality have to evolve with it?